Okay, team, here we are ready for week 2. I just want to address a few things and then we'll dive into the lecture. We've got a lot to cover today. First off, I want to apologize for the assignments and the quiz last week. The problem with knowing the answers is when you go through and test it, and trust me, I went through it several times, I already know the answers. It's very easy to not see a flaw in the question. Like, say, you don't know that bending and moment is bending moment. So that's not apparent to you that that's a method of strength or a type of strength design that we have to look into. It's a type of force. Me not noticing that live load or snow load is missing from the question. Not very apparent to me because I know the answer. And then there was 2 or 3 where it appears that I used the wrong deflection criteria. What happened is last year, late in the term, I became aware that sometime over the past year, the different codes, which are now in effect, so the codes get published, but they don't come into effect until the National Building Code, until the Ontario Building Code adds them in. All of the material codes had done small adjustments within their deflection criteria tables. And then there's also what is in the code and what people do as good practice. And so sometime late last year, I had revised and updated that deflection criteria table. So the table you have is correct. Some of my questions, I was using the old tables. So that's why some of those values are going to come out wrong. That the second part to all of this is that normally I have the TAs vet these and go through these very diligently and make sure I'm not doing anything silly or ridiculous like I did this week or last week. We didn't have our TAs yet by the time this went live. I think I had gotten them 2 of them a couple days before, but even then things weren't locked down, so the TAs didn't get the opportunity they would normally have to go through it. And even then there's supposed to be 5 of them, and we only had 2 of them and they didn't get the time they needed to go through it. So hopefully things like that aren't going to be the norm going forward. That said, if I make a mistake in an assignment and quiz, you will not pay the price for it. I would have loved when the very first information came in that, Shannon, you messed up the assignment. I wish I could go in and fix it. But the problem is anyone who already has it open won't see the update. And then we have a hard time going in and editing the marks to give people the proper answers or proper marks for the wrong answers. So your TAs are very diligent. They're going to go through everybody's assignments and assign the marks according to if they chose the wrong answer that to you guys looked like the right answer. So don't worry, you're going to get your marks, and the TAs on Friday are going to go through the answer sheet with you. So they're going to work through it. It's also going to be published on Quercus on Thursday. So you guys are probably watching this on Thursday or Friday, but the answer sheet for the first week's assignment and quiz will be made available to you. That's something I didn't used to do. I used to make it that you had to be in the tutorial to get the correct answers, simply to encourage people to write them down. I know that for many people, the act of writing it, visualizing it, helps lock it in your brain. But with the pandemic, last year I posted them because there was no in-person method for that, and it seemed a bit harsh to try to do that over Zoom. This year, I think I'm going to stick with posting all of those answers. Anyone who doesn't feel comfortable coming into the classroom, I don't want them to have to come in if they don't feel comfortable with that. On that note, tutorials are not mandatory. They are a voluntary place where you can go and ask questions of your TA. Also try to remember that there are 5 TAs and 1 of me. If you have a question about whatever it is, make sure you reach out to your TA first. If they don't have the answer, they will certainly send the question along to me. But I should see that this question is coming from the TA, or maybe something has happened. If it's a more private conversation, then definitely reach out to me. But if it's something about the assignment, how you're supposed to proceed with something, timelines, anything like that, you should definitely be reaching out to your TAs. One of the questions I did get was, what are loads? How am I supposed to know what these loads are? Well, last week you didn't need to know. You just needed to look in the question what load I was talking about and reference the table I gave you for those load types. This week we're going to talk about loads. We're also going to talk about what the heck structural drawings even look like. So I have created two fake buildings. They're the same building, one in steel, one in concrete, that I have created a set of structural drawings for that you can look at and as a reference going forward to kind of see what I'm talking about. I've also posted to Quercus in the helpful drawings module. It's called something like that. I can't remember the exact name of the module. But there are drawings that some architects, there's a stupid fly in here, that some architects from Ontario have volunteered to allow me to post their drawings for you to reference, where I have also posted my structural drawings, so that you can see kind of the parallel. What's the difference between the structure and the architecture on a set of drawings, to try to give you that ability to look at both of them. So today, we're going to look at the drawings, we're going to look at loads, and then we're also going to look at how we combine those loads to get that load side, or that factored load side of our equation. And then we're going to talk about tributary area and tributary width. So this is basically how much of something loads up another thing. And this is where I think intuitively most of you have a good sense of these things. For example, I have this table right here. If we can look at it like this. I have this table. If I asked you what percentage of this table went to this leg, and what percentage went to this leg, and what percentage went to that one, you would know that it's about 25%. You know that if I sat in the middle of this table, half of my load is going to this side, and half of my load is going to this side. You intrinsically and intuitively understand tributary areas and tributary widths. We're going to talk about that, and we're going to do some quick calculations that look at those. So we are going to do some calculations today, not a lot, but we will do some. So let's start digging in here. So I've already commented on this. So I have posted for you Varsity Gold Ring Center for High Performance Sports. The architect, MJMA, and PATCOW have allowed me to post their drawings for you, and the structural drawings that I did when I was at Blackwell. If you ever get the opportunity, go check out that building. It's gorgeous. Cube Lofts was done in 2007, and it was a unique project in that we did it out of steel because that was economical and it made sense for that project. We tendered the project, which means we send it out in the world and different contractors say how much it'll take for them to build it. In that 3-month time frame, the steel commodity prices went bananas. Now, that was an unusual circumstance back in the day, and I've talked about it for years, but we're seeing that same thing with wood and pretty much all building materials right now. Then it was because of the Beijing Olympics. So a huge portion of structural steel in the world was going to China for mass construction. And the prices in North America for a period of 3 months almost doubled. So we had to redesign the project in concrete. Some small architectural changes happened in that time, but not many. By the time the concrete project was actually tendered, steel had dropped back down and it would have been cheaper to do it in steel. But we have 2 sets of drawings for that project now. So those are all available on Quercus. All right, structural drawings. Now, a lot of this terminology, so these are some of the common abbreviations. This is in the typical details PDF, which is also available for you on Quercus, both in the downloads section and also in this week's module. So I have it in there twice so that you can't miss it, hopefully. So this is on the typical details, and I'll show you the typical details. Actually, why don't I pop this up right here as well. So this is my typical details for abbreviations. So you can see that we've got some common abbreviations here. I'm going to go back to our lecture, because I have identified some of the ones that are going to be really important for us in this course. C/C means center to center. So how often does something occur? Or on center, OC. CANT period is cant, which is the abbreviation for cantilever. CA means column above. GA usually means gauge. KN, kilonewtons, that's going to be a unit of measurement that we are going to talk about in a few minutes. MC is moment connection, or MOM is moment. This is that bending force that we talked about. So if this is bending, it's also called bending moment. So we refer to that bending force as moment. I realized in last week's lecture, to me, bending and moment are the exact same thing, and in the lecture slides, I referred to it as bending, and then in the assignment, I listed it as moment, and you obviously couldn't have known that, or some of you did know it, some of you did figure it out, but it's not really fair that anyone would be penalized for not knowing that. Open web steel joist. OWSJ. I'll show you an open web steel joist in just a second. R for reaction. SOG is slab on grade. And U/N usually means unless noted. So we'll say something's typical unless noted. The ones that are really important in this course is, you can see here, this says a big C with the sub F. That is our factored compressive force in kilonewtons quite often. So C for compression, and that sub F, that means we factored it. Same for MF, that means our moment is factored. We have VF, that's our shear, is factored. Any of those with the subscript R also means reaction. And this one is tension, so TF is our factored tensile force. We're not going to do torsion, but factored torsional force is listed there. All right, if we are cutting through something in a section, so if I was looking at a plan of this table, so I have a plan of this table, I'm looking down at it, that's a plan drawing. If I have a section, it means I'm cutting through this table. Anywhere I'm cutting, so if I have a section right here, looking that way, I have cut through the table material, but I'm looking at the legs beyond. So anything you cut through, you would hatch it. And hatching it means you draw it in to say that you've cut it. And the hatching can give you an indication of what the thing you're cutting is. Geotechnical basically means earth materials. So earth, fill, gravel, sand, or rock. Concrete and masonry. So if we're cutting through brick, it is a tightly spaced 45 diagonal hatch. If it's block, it's the same hatch, but spread out a little bit. If it's cast concrete, you'll see little triangles and dots representing rock and sand. If we're doing it at a really high scale, like 1 to 100, we might just show it dotted as sand, similar to our grout that we're showing here. If we're talking about a detail, we'll draw the reinforcing, or the steel within the concrete, or a reinforced concrete. These are just quick to tell you what the things you're looking at are. Metal, mostly steel, is a diagonal hatching where we have two lines tight together and then a space and two lines tight together. So here we have a W section, an HSS, a channel, and an angle. If you're thinking, what is she talking about? That's going to come later. We'll look at what that means in very focused lectures. What exactly are all of these? Wood. Wood, we often, for a wall, would draw it with a little squiggly, so if we're cutting through a wall. If we're cutting through a section of a member, we would draw it with an X on it. So if this was a 2x6, and I've cut it right here, we would draw an X on it. And plywood, we do 4 tight lines and then a space. Okay, so I have created, I've called it a typical building. It is not a practical building at all. I am definitely not an architect. My building is a very bad plan. It is a very bad idea, but it is structurally sound. I have done an analysis on it, I have a model of it, and I have sized everything, and I have drawn it for you. So the things I really want you to be aware of, and I'm going to open it up in the PDF, but the things I want you to be looking for: the grid identification, grid dimensions, labels. We label things. What are the size of the elements that make up the building? Remember, the whole point of these drawings is to be able to tell someone how to build the building. I should be able to hand over my set of drawings and walk away and never look back, and somebody should be able to build it. They should be able to know what me as the engineer and you as the architect came together to draw to be built in the real world. What the framing is, we should be showing the gravity system in plan. We should be showing the lateral load resisting system. What's the lateral load resisting system? That's the thing that stops it from tipping over. And we should be showing the cantilevers. Actually, I just want to see if I have right here. Okay. So, lateral load resisting system. Here's a frame that I built out of my kids' toys. What happens? It just wants to flip over. It just wants to fall over. That's because it has no lateral load resisting system. If I put this brace in it, it's the exact same one, but this one has a brace in it. I can't push it over. It's stiff. We also have diaphragms, which is in our floor. So this is a floor. If wind blows on it, you can see it can still skew in plan. Well, we wouldn't normally do a brace in plan. We would put something stiff on it, like plywood or a deck. But that's what I'm talking about when I'm talking about lateral load resisting system. This has no lateral load resisting system. This does. So we would show that on plan. And we would often identify cantilevers. So cantilevers are, so this is supported at both ends. This has a cantilever. I've pulled the support back, and this part right here is a cantilever. All right, let's take a look at our steel drawing. So typical steel building. All right, so this is my steel building that I've created. It's Hilchian Engineering. I have all of the information. I've labeled what it is down here. I've shown what it is, what drawing that number it is, and the intent of what I'm showing. Let's come out over here. This is the foundation plan. So this, if we have a building, I am, for the foundation, cutting just above the foundation and looking downward. I feel like the next thing I'd love to, each year I add a little bit to these drawings. I have, you know what, I'm going to flip to a section just to show you what I'm talking about here. My foundation section, or my foundation plan, is a line right here looking down. My second floor plan will be a line here looking up. All right, so foundation. I'm cutting just above my foundation and looking down. So there's a huge zone that's unexcavated. It looks like right here we have no basement. We have nothing here, but look at this. Over here, we have a basement right here. So this is a 150 slab on grade. So slab on grade is the thing that sets directly on dirt. We have grids, and we have the dimensions between the grids. We have concrete foundation walls and something showing SDF. That's a step down footing. We have these foundations here. Let's take a look what it says about our foundations. We have notes down here as well. So found footings at the geodetic elevations shown in plan, all footings to be a minimum 1.22 meters down for frost protection. That is standard in southern Ontario, and we'll talk about that later in the term. But that means these foundations here are down just below grade, about 1.2 meters down. But these ones need to go down deeper because we have a basement. So we have to dig down deeper. We don't just go along and do a straight line and go down. We have to slowly transition down to that deeper footing. So that is indicated here with a step down footing. So we have piers on footings, and I'm going to show you sections through this, and you should be taking the time to take a look through these. You know, the intent is that you're already comfortable and familiar with drawing sets, whether it's architectural or structural. The assumption is already that you can read them. I think that's a bit of an ask to assume that you already know all that. So that's why I'm taking this time to go through this, and that's why I've drawn these drawings. So saw cutting, it's about crack control. I've just put so the dark notes are the things that would normally be on a drawing set. The grayed out notes, or the lighter ones, were ones that I just thought might help you understand what's going on. So I've taken the time to kind of indicate it there to benefit you in some way. All right, the next plan is our ground floor framing plan. So we're cutting just below the ground floor and looking up. So before we were cutting and looking down, and now we're cutting and looking up at the ground floor. Here, when we were looking at the foundation, there was no basement, so we were cutting through dirt and looking at the foundations. Except for where we had a basement and where we had our stairwell going down to the basement and our elevator pit. Here, we're cutting and looking up at the ground floor, or something called a reflected ceiling plan. So we're cutting through our concrete foundation walls still, so we're still somewhere down in the dirt, but now we're cutting and looking up. We have our elevator here and our stairwell here, and you can see we have doors here because we're cutting through, so we're not cutting through a hatched part anymore because there's a doorway there. All of this zone now is our slab on grade. So that's some concrete sitting right on dirt. It's supported everywhere. So instead of being our table like this, it's if we took the legs off and set it on the ground. It is fully supported everywhere. Over here, above our basement, we have 64 concrete on 38 metal deck. Now, there's a lot of terms I'm going to throw at you here, and you're not going to know all of this information. We are going to go through each material in a separate week of, I think we spend 2 weeks per each material, where we look at what's typical, what all of these terminologies mean. Right now, I'm just trying to show you a lot of information on the drawings. We're not going to stop and explain it all. This will be helpful when we come back to it, when we start to talk about structural steel. The idea here, though, is that I've labeled this. The metal deck spans from here to here, and then from here to here, and then from here to here. So it is like, well, you know what? I have a piece of paper right here. I am going to do something that looks very similar to my metal deck. All right. So I've badly folded this piece of paper. Paper by itself doesn't span a very far distance. Paper like this wants to crumple like this. Paper like this, because I folded it, is now very stiff. Look at how far it goes without trying to crumple. Turn it this way and it tries to crumple. That is the idea of metal deck. This is the direction that it spans. So this is matching the arrow here like this. This deck would get supported on a series of elements. So I'm going to be very weird with this. All right, so the deck would be spanning. We're going to be really weird. All right, so we would have, if this is our deck, we would have something here, and something here, and something here, and something here, and something here supporting it. So it comes in one big long piece, but this, if this represents my pen, is picking up this amount of deck. And this beam here is picking up this amount of deck, because the deck is spanning in this direction. We will talk more about that later today, and again when we talk about each of these specific materials. So we have notes here. We have a column schedule that shows us our columns. So we have what size it is. We have it labeled. So look at this, A2, column at A2. Let's find where A2 is. So it looks like we're talking about this spot right here. See this CA? That means column above. So it looks like our steel column starts somewhere around the ground floor and goes up. Let's verify that with our column schedule. Look at this. Oh, our column starts right here, just around the ground floor, and goes up just to level 2. So let's look at our second floor plan. So this is cut looking up now. So we have our big space here. We have our elevator and our stairwell here. We have a few things happening here. It looks like we have an outline of our building right here. This dashed line is our architectural line showing us the extent of our building. It looks like this zone here is a roof, and this is a floor. So it looks like this is a low portion on our building. We have something here. It looks like this is our snow load. This is representing our snow load. We have beams and something called a purlin here. Ooh, look at this. Column above. That seems like it's going to be messy. We have this 2B13 spanning from one column all the way over to another column with a column above on it. That looks like that beam is doing an extra big hard job. We will reference that when we start talking about how we estimate sizes of things. Over here, we have something that says 240 masonry block LLRS, or lateral load resisting system. Remember how I said it could be a braced element? Well, it could also be that we have not just something floppy like this. I wonder what are the odds that my calculator, oh, look at this. So my calculator fitting in there stops that from racking as well. Imagine if my calculator fit in there perfectly. It could be a shear wall, or it could act as the lateral load resisting system. So when we build solid walls, out of a material that we can use as a lateral load resisting system, we often do that. So plywood on wood framing houses, for example, block and concrete walls in buildings we would use as lateral load resisting systems. It looks like we also have these dashed lines here. This says steel bracing, with bad spelling, lateral load resisting system. And it tells us what size it is. Oh, look at this. CF equals TF equals 50 kilonewtons. Or the factored compressive load equals the tensile factored load equals 50 kilonewtons. What they're saying is that whatever load is acting on this could go this way, or it could go this way. So if it's trying to go this way, it's going to squish this column, or this brace element. If the load is going that way, it's trying to pull. Oh, look, I actually broke it apart. I actually pulled it apart there. So it's trying to pull it, and that would be our tensile, or our tension factored load. See these dark triangles here? That is representing a moment connection. And look, we have CANT, or cantilever. So it looks like this beam comes along, gets moment connected through here, and cantilevers out here. We can do two things. If this is going to represent a beam now, when we have a cantilever, we can continue it over the top of something, and it cantilevers over. Or we can break it apart, and at that point, connect it back together. Why would we connect it? Why would we break it apart and connect it back together? Well, sometimes maybe we want that cantilever bit to be a shallower piece, and we need to moment connect it and then support it. That is exactly what's happening here. See this cross line? It says minus 250. This zone here, the underside of the metal deck, is dropped 250 millimeters in this zone. Again, I know I'm saying a lot of words that you don't know. Take a breath. You don't have to know all these yet. I want you to start hearing them, but you don't have to know them yet. My 5-year-old has just started French immersion this week. He knows no French. And so I'm highly aware of how just hearing it get repeated is how you can learn. I'll also take the time to teach you, but I can't teach you everything on day one. So I'm saying a lot of things that you haven't learned yet, but by the time you learn them, they'll already sound familiar. All right, we have a beam schedule here. So these are the labels that we have, and they tell us what size section we have here. We're going to talk all about this and what these things mean. Look at this. We have reactions in kilonewtons. And if we look down here, it says the design connections for axial force, PF, end moment, MF, torsion, TF, or out-of-plane horizontal forces shown in the remarks column. In addition, the vertical shear is in the provided in the reaction column. And so these are all factored values. And so this says 2P01 is a W150 by 24. Let's go find our 2P01. Oh, look at this. This is an element that spans from 2B01 to 2B03. It looks like it's supporting metal deck that spans in that direction. Here we have our roof plan. So we have RJ01. See this funny dashing? We have a double dash. That is often the dashing we use for joists or open web steel joists. And I'm going to show you what that is in just a minute. So take the time, look through these drawings, read them. I'm not going to go through every single thing. What I have added this year is sections. So if you go back, you can see this is a section mark, so I'm cutting through the building, looking that way. I'm cutting through the building, looking that way. I'm cutting through the building, looking that way. Here are those sections. So you can see this is the one where we had our ground floor or our foundation cut looking down, and then we cut looking up, we cut looking up, and we cut looking up. We have our next section where we actually cut through the elevator core. And you can see we have an elevator pit here that we called up on the plans. And here's one where I show that moment connection through that column where we have a cantilever. So nothing picks up the end of this. So if we have nothing picking up the end of it, it can't be just a pin. It tries to fall over. We need something that grips it and stops it from trying to rotate or spin in space. And that's our moment connection here. But we couldn't just bring this one beam across because we needed it to drop down. Here's our basement. There's the slab on grade that we had at ground level. Here is our concrete on metal deck and beams that we had at the ground level over a basement. And here are our open web steel joists. So these are at some regular spacing. And this is what an open web steel joist looks like. We're going to talk about all of these when we look at steel. You can see this open web steel joist and this beam are sloped down to a point. If we can, and it's simple, we will slope the top of the structure to help the architect to achieve their roof drains. Water wants to go to the lowest point, and so we build that in. And I'll talk about that a little bit when we get to loads as well. So that's our steel set of drawings. You can feel free to go through this on your own and take a look at them. This is the same building as a concrete building. I will point out that with the steel, what we often do is we make our grid lines run through the center of our steel. It makes detailing and coordinating so much easier, and we reference everything out from that. Concrete will often bound the edges of the structure with our grid line. So here in the center, no problem, we go through the center of our column. But at the edges of the building, our grid line often aligns with the outside edge of our structural elements. Here is our ground floor plan where we're cutting just above the foundation and looking down. Most of it looks the same for this building. Our pier is a little bit bigger because we're picking up a concrete column above, not a little steel column. But for the most part, this plan is the same. Even this one looks similar, but instead of CA saying column above, we can see that we have something else up there. We have a concrete column up above. The slab on grade is the same. Instead of having metal deck on beams that then span to the edges, we have a one-way slab, or a cast-in-place concrete floor. It spans from here to here. Basically, we would have rebar going in this direction doing the majority of the work. Here is our level 2 plan, so we're cutting just below level 2 and looking up. Instead of masonry as our shear wall here, we have concrete. If you're building a concrete building, you're not going to take the time to do a masonry wall. We have a concrete building, so we're going to cast concrete cores for this. We have our column above here, same as we did before. So that means we need a major transfer concrete beam. One of my spelling mistakes. They would be preliminary sized as a girder. We're going to talk about what a girder means in a few weeks. We have our dropped down area for our balcony, and we have our dropped down area for our low roof. Here is our high roof, and we have drop panels, and we had capitals over here. So that is all about shear. I'll show you what that looks like in section. Let's go to our sections. So a drop panel, I'm going to go through one. Okay, so Here is the outline of our major transfer beam picking up this column, and here is our drop panel. This section is just before cutting through these beams and drop panels. So we're seeing the beam, we're cutting through the slab, and we're cutting through this beam, and we can see the beam parallel to our section beyond, and our columns beyond, and our drop panel beyond. So again, these are here as a reference. This was just supposed to be a quick intro. The idea is that you're supposed to know all of this, but I don't really think it's fair. So I've made these. You can go back and take a look. And sometimes, just if you're really having a hard time understanding what I'm talking about, go back and take a look at these drawings. It might make it clear what we're trying to do with our structure. The last thing I have in here is our typical details. So I already showed you the abbreviation typical detail. I have provided you with 126 typical details that you can take a look at. If you want to see how things normally go together, and that's the idea behind typical details, it means it's typical, it's normal, it is what is done the majority of the time. You can go through and take a look. Let's just pick a random page here. Let's go to page 50. Well, that one's a somewhat unusual one still even. I want to get to one. Okay, so here is a concrete column. You can see that we have the reinforcing in our column. They're talking about how it's reinforced. There's bottom of a beam beyond, or the slab, or the capital, that's beyond. So that could be a drop panel. So I drew mine dashed just so it didn't draw the eye away. They drew it as a solid line here, but we're cutting through everything hatched, looking at something beyond. So this is really where we might get into some more refined details of those things. And then we would also have sections through our building. So each year I'm adding a little bit, so next year I'll probably add 2 or 3 sections to around the building of my typical, not typical building. Let's take a look, let's go a little bit farther, maybe we can get into the steel ones. Okay, so here we're in steel. Well, look at this, we have steel deck framing. We have steel beams with open web steel joists. We have steel beams with metal deck on it. So steel beams with metal deck on it are tucked up tight to the underside of the metal deck. Steel beams that are picking up open web steel joists get dropped for a joist shoe. So you can see here that we have something called a joist shoe. And so beams that are picking up a joist get dropped a little bit. Let's just go take a look. I'm going to go back to my beam schedule. It looks like this 2B13 is picking up open web steel joists and open web steel joists. Let's look at my beam schedule for 2B13. 2B13 was a W610 by 153. These are our reactions. And see this minus 100 here? The top of beam is down 100 millimeters from where you would normally put a top of beam because it's picking up the joists. Okay, let's jump back to our slideshow. So we looked at our typical steel building and our typical concrete building. Here's just an image of some open web steel joists. And then I just talked about the typical details. Okay, let's dig into loads. We have a lot to cover today, and I do want to do a few examples. We're probably going to go right to the end of our 2 hours today. There will be a lot of lectures where we're not the full 2 hours at all, and there's 1 or 2 where we might go 5 minutes over. That said, if we go over, it's because we have a lot of examples, and the people that don't need all of the examples don't need to listen to all of it, but the people that really benefit for it, think of it as me providing you with extra resources. So not all of it is required in the lecture time slot, but I've added in places where I see that people who maybe struggle with certain things could use a little bit of benefit. So let's start with loads, live loads. I have provided you with a live load table, It's in this week's module and in the downloads module. Live loads are the people in the building. It's us. It can mean some elements within it, like some desks and chairs and things like that, but predominantly it's people. We have it broken down into several types of loads. We have assembly and all kinds of other ones. You will see, well, actually, I meant to have all of those open. Let me, I'm gonna open it up for you. We might as well. My mouse is super huge because I need it so you guys can see it. So just bear with me for a second while I open the live load resource for you here. I changed my filing system just a tiny little bit. Okay. Live loads. Okay. So here I've provided this for you, the OBC, which is the Ontario Building Code 2012 with amendments, live loads. So we have right here assembly loads. All of this category is considered an assembly load. So we get to use, sometimes it's 4.8 kPa, sometimes it's 2.4, sometimes it's 2.9. We're going to talk about that in just a second. Let me bring our lecture back up. So we have assemblies, we have all kinds of different types of buildings. The live loads, really, I looked them up in a book. In fact, I believe the book is sitting right here. This one is the National Building Code of Canada, but it's the same idea for the Ontario Building Code. It's actually two binders. Two of these is the code that we're talking about. And within that is where that table came from. You and the client are designating the use of the building. And based on that use, I can then pick from that table what live load is the applicable live load. So before we talk about what the live load is, let's talk about what a kilonewton means. So what does a kilonewton mean? A kilonewton is 225 pounds, thereabouts. It's pretty darn close to 225 pounds. It's like 224 point something, but 225 will do for our use this term. This guy weighs almost exactly 1 kilonewton. I went through to try to find other people that I could use. Channing Tatum, he's a little dude. He's super muscly, but he does not weigh 225 pounds. I tried The Rock, and he's huge. He weighs way more than 225 pounds. So we're going to stick with Arnold as our representation of 225 pounds. This person, I am not in touch with anything. The last supermodel I was ever aware of is Kate Moss, and she was around 112 pounds. I in no means endorse the culture of supermodels starving themselves. I feel strongly that supermodels should weigh a lot more than this. They shouldn't weigh half a kilonewton, but we're going to use this as our resource at the moment. So Arnold is 1 kilonewton, and our supermodel is half a kilonewton. Me and some of my hockey pals, let's say we all add up to 2.44 kilonewtons, something like that. So you can see that if you know it in pounds, you can convert it to kilonewtons. What does 1 kPa mean? Well, a kPa is 1 kilonewton per meter squared. So if you take that 1 kilonewton load and spread it out over 1 meter by 1 meter squared, you've got 1 kilonewton, or 1 kPa. So if we take Arnold and put him over 1 meter by 1 meter squared, we have 1 kPa. If we wanted to achieve 1 kPa with the supermodel, that one supermodel over a 1 meter by 1 meter, she was half a kilonewton over 1 meter by 1 meter squared, giving us half of a kPa. 2 supermodels, or 1/2 of a kilonewton plus 1/2 of a kilonewton over 1 meter by 1 meter squared gives us our 1 kPa. So that's what we're saying. We're saying we have a load and we're spreading it out over an area. Or every 1 meter by 1 meter zone can take that many kilonewtons, or needs to be able to design to take that many kilonewtons. An assembly area is 4.8 kPa. So we're saying 4.8 kilonewtons needs to be over that 1 meter by 1 meter squared. We need to be able to support 4.8 kilonewtons on every 1 meter by 1 meter area of that floor. So if we have 5 of these squares, well, each one needs to be able to support 4.8 kilonewtons, and so we'd be supporting 5 times 4.8 kilonewtons, or 24 kilonewtons. So we have 4.8 kPa over 1 meter by 1 meter. That is 4.8 Arnolds over 1 meter by 1 meter squared. If we were talking about our supermodel, we would need, 9.6 of our supermodels, because remember, they weigh half of a kilonewton. So we have 9.6 times half a kilonewton would equal our 4.8 kPa. So we need to be able to design this floor so that every 1 meter by 1 meter section could support 4.8 Arnolds or 9.6 of this particular supermodel. That's what we're talking about. That's what we need to support when we're talking about an assembly load. This is pretty much an assembly load right there. I often say, is this comfortable? I used to, when we taught in person, at the beginning of this lecture, would tape off a 1 meter by 1 meter square on the floor. And before I'd start the lecture, I would ask 3 other students to come up, or 4 other students, so 5 people in the 1 meter by 1 meter square. It was tight. It was a little awkward, but not too bad. And then I would say, okay, but I don't think any of us actually weigh 225 pounds. Probably the average of us was each probably like 150 or 175, somewhere in that range. So I would say, let's bring up 2 more people. So 7 people in that 1 meter by 1 meter squared area. And it's tight. It's not a comfortable way to stand. And this was pre-COVID, where it's illegal to do that now. It is a tight spacing. So 4.8 kPa is an extreme load. It isn't the norm, but if anyone remembers what it was like to take the subway, or if anyone was here when the Raptors won, you know that it is not the norm, but it is achievable. We're not comfortable in that spacing. We don't love it, but it happens enough in certain buildings that we have to be able to design for those loads. So let's take a look at a few other types of situations. Bleachers, stadiums, and grandstands are an assembly load and need to be designed for 4.8 kPa, which can happen. Look at this. This is when the Jays won. I think it was when they won one of the division series. I don't think this is 93, way back in the day when they won the World Series, but you get the idea. Assembly areas for fixed seating, except stadiums. This assumes you don't have people standing and jamming themselves in around the seats. The seats actually take up enough space that you can't get 4.8 kPa. So we would use 2.4 kPa. Dining halls. We say if it's under 100 meters squared, we can use 2.4 kPa. If it's over 100 meters squared, we've got to use 4.8 kPa. And why that difference? Well, I have been in several dining halls where you sit, you eat dinner, and then you go outside, you take some pictures, and you come back, they've cleared the tables, and the DJ is playing the music now. And in that situation, if it's a big enough room, if you play music, they will come. So you need to be able to design, you need to design those ones to support 4.8 kPa of live load. Non-assembly areas. So an office building is a really good example of that. For an office building, we do 2.4 kPa on the upper floors and 4.8 on the lower floor. We consider it not an assembly area though. That is because, well, we have something, well, I'm not going to get into it. There are times where we use the criteria of whether it's assembly or not to apply other factors to things. That goes beyond what we're going to do in this course. If you stick around and join my graduate program, we will talk more about that. But we're not going to go into what that differentiation is right now. You will come across in the assignment and the quiz some other listings on what you should pull from that assembly load. Don't go rogue. Don't look up your own lists on the internet. Every code is different, and we are using the Ontario Building Code of Canada and the list I provided you. You should not be looking up what it is in other places, because in some places that develop their codes, so 4.8 translates almost perfectly to 100 pounds per square foot, which is how we used to design, was in Imperial. The codes that were just developed straight up in metric the very first time, they use 5 kPa quite often. So we had to pick a code. We're going to use the one that's here where we're learning. I know last year some of you weren't here, but that's what we're doing. We're going to use the one in our jurisdiction. They're all similar, but we're going to use ours. So use our loading table that I have provided for you. Why would we worry about 4.8 kPa? Normally we have foundations and this would be a slab on grade. Who cares if this is such a high load here? It's sitting right on the soil. Well, for a lot of these office buildings, especially in downtown Toronto, some of you might have taken the PAC system, where what we have is a big open area under our building. And sometimes our building setbacks are just for what's above grade. Below grade, you can usually go right to the property line. So this needs to be able to support 4.8 kPa. Residential live loads. When I first started teaching this course, residential live loads had two categories. Bedrooms were 1.4 kPa, and all the rest of the house was 1.9 kPa. I don't know what studies and research they did, but they decided the bedrooms needed to be increased to 1.9 kPa. But in 2012, they increased bedrooms to match the rest of residential live loads at 1.9 kPa. Vehicles have a live load associated with them. So parking garages, that makes sense. We'd have cars with 2.4 kPa. Parking garages with buses and light trucks, 6.0 kPa. Parking garages with heavy trucks would be 12 kPa, so something like a fire truck. Driveways and sidewalk areas and basements, 12 kPa. Why would we want a vehicle allowance for driveways and sidewalks? They're right on the ground. Well, when we look at soil loads, we'll talk about that. But if any of you have ever dug a hole in the sand at the beach or in the dirt or in a playground, and your pesky sibling has come along and stood on the edge of that hole, the soil tries to fall into that hole. It was perfect, it was fine, it wasn't trying to go into that hole, but you put a surcharge load on it, or a load right beside it, and the soil tries to go into that hole. And that is why driveways and sidewalk areas around basements are something that we worry about this load. If we have a laneway right beside our basement, that heavy truck is trying to make soil go into the basement, and so our foundation wall needs to be designed to resist it. So dead loads. let's talk about dead loads now. So we've talked about live loads. I'm just trying to catch up here because I'm going to do a thing in a minute with you guys. So, dead loads. Dead loads are the thing that make up the building. You don't care too much about this differentiation between self-weight and superimposed dead loads. I do when I'm designing because my models will sometimes separate self-weight and superimposed dead loads. But for us, we're going to talk about it all clumped in together as dead loads. Dead loads are all the things that make up the building. You, as the architect, have a lot of control over the dead loads. So I have provided you with a dead load sheet the same way as I have the live load that you can look at and reference. You should know how to look these up and add them up for a total dead load for a floor or roof if somebody gives you the assembly makeup. So let's take a look. We have steel decks. We have concrete all by itself, but then we also have deck slabs. So these are ones where we have concrete on top of metal deck. And this is what we would call our composite deck or concrete on metal deck. Let's take a look at, I think the best way to kind of look at this is let's go through one of these. So we have 4-ply with gravel roofing. We have 6 inches of rigid insulation. We have 38 millimeters of metal deck. We have open web steel joists. We have steel. We have a mechanical electrical load, and we have a suspended load. A lot of these don't mean much to you yet, but we can go back and find these in our dead load allowance table. So 4-ply with gravel. Let's come, I'm gonna, you know what I'm gonna do? I'm gonna open it in this. So let's make this as much of my screen as I can. So 4-ply with gravel. We'll look at this section. Roofing. We have 3-ply asphalt with no gravel, 4-ply with no gravel, that's not right. Oh, 4-ply asphalt and gravel. 4-ply asphalt and gravel. It looks like that weighs, in kPa, 0.32 kPa. Okay, so that's part of it. We've got some of it now. 6 inches of rigid insulation. Let's go back to this. It looks like we have an insulation section right here. So insulation per 100 millimeters thick. Well, we have glass fiber rigid insulation. If it was rigid foam, I'd specify that for you. So we have 100 millimeters. They told us we had 6 inches. Well, 4 inches is about 100 millimeters. We have about 150 millimeters. So if you guys remember, an inch is 25.4 millimeters. So our 6 inches times 25.4, or 6 inches times 25.4, equals 152.4 millimeters. Every 100 millimeters weighs 0.07 kPa. We need basically 1.52 times this, or 152.4 divided by 100 times 0.07. Or, maybe I could write it out here. It's a little bit hard to see because I'm looking at multiple screens. 0.10. Okay, and then let's look at our slide again. 38 metal deck. Okay, let's go to our, I'm gonna use my highlighter. Sorry, my screen screen that I'm looking at over here is absolutely fried. So I'm trying to look at the wrong screen to do this. Okay. Steel deck, 38 millimeters deep. There's two different thicknesses. I'm going to tell you that this top one is normal. This is normal. So we've got 0.1 kPa for our metal deck. All right, let's see our next thing. Open web steel joists. Ooh, this one's a pain in the butt. We don't know. We haven't designed it yet. We can't know what it weighs to design it until we've designed it and know what it weighs. So what we often do is make a reasonable assumption. I won't make you pick that. I will tell you what to use there. So I am going to tell you a reasonable amount to use for the open web steel joists, and we're going to assume 0.15 kPa. Same with the steel. We don't know what steel numbers we're using to know how much they weigh to be able to use their weight in our design. So we're going to say that it is 0.2 kPa for our weight of steel. Mechanical and electrical. Let's go back to our PDF here. So let's take a look at this. Ducts, pipes, wiring, allowance, average condition. So that's all of our mechanical, is our ducts and pipes, and our electrical, which is our wiring. 0.25 kPa. And then the last thing that it had listed there was the suspended ceiling. So let's take a look. Tiled ceiling and suspension system with fixtures, average. So this is your normal crappy dropped T-bar system. If you've been anywhere kind of institutional recently, you've probably seen that style of roof. And it is 0.2 kPa. So we have our 0.32, our 0.11, our 0.2, our 0.25, our 0.1, and then the 0.15 and the 0.2 that I told you to use. Let's go back and write those out. Oh, come on, mouse. Here we go. Okay. So let's take a look. We have our 0.32 for our 4-ply gravel, our 6 inches of rigid insulation. I suppose we could have rounded up or down there. If I had used 150 directly instead of 100 times our 0.07, I would have gotten I would have rounded down there. If this is something like this in the assignment, I'm going to make a note to myself to double check. Double check the rounding. I always go through and check everything assumed rounded down, where we have the option to round, and everything assumed rounding up. I look at that boundary and I build that buffer into the answer. I would put this answer as 1.32 plus minus 0.01. So that if somebody had rounded up with this and it was 0.11, they would still get the right answer. So we have all of these elements that we've added up, and we can figure out the total dead load to use on our roof. Don't worry about this. The thought here is that the deck is sitting on top of the open web steel joists and the steel. So it isn't supporting the open web steel joists and the steel, or the mechanical or electrical, or the suspended. It is supporting itself, the rigid insulation, and the roofing material. So the deck, as much as our steel members would be designed for the total load, our deck would only be designed for this load. Our open web steel joists are supporting the metal deck, which is supporting the insulation and the gravel, and the mechanical and electrical would be hung off of the joists, and the suspended ceiling would be hung off of the joists. So it, though, the open web steel joist would not support the steel. The open web steel joist sits on the steel. So it would be designed for 1.12 kPa. Again, we're not going to do that. I'm going to stick with total values for you guys. So don't worry about that too much. I just wanted to explain that different layers within an element can even still have different loads. Importance factors. Importance factors rate the importance of that building. Most buildings are normal. Unless you're told otherwise, your building is normal. When might they not be normal? Well, we have low importance buildings. So those are the ones that if no one's in it and it collapses, nobody's likely to get hurt. I can tell you that I have only designed a few low importance buildings, or not really even any buildings, elements. I usually assume that it's a normal importance and would only switch to low if it met the criteria and we were really pushed in the design. Like there would have to be a good reason for me to not design it as normal. Unless it's high or post-disaster. High importance is anywhere where people might gather after a disaster. So, for example, a community center. It doesn't have to function as a community center. People aren't going to go play hockey. You're not going to go swimming right after a disaster. But people will gather there after a disaster. If you think about places that experience a hurricane or a tornado or flooding, you will go to that place to seek shelter if something happens to your place. You're not expecting to play a football game in there, you're expecting to go seek shelter. Post-disaster buildings are ones that need to function as they were intended even after a disaster. Things that are post-disaster: police stations, hospitals, fire stations. You want those to function as their intended role even after a disaster. You want those to be functional no matter what happens. I say you want them to survive the apocalypse. Other things that might be would be communication centers or communication hubs. Post-disaster, radio communication and television communication is very, and cell service is very, very, very important. So those are also considered post-disaster. I'm going to tell you that unless I tell you otherwise, you are going with a normal importance building. What are the importance factors? I have gathered them up from the different sections in the code because wind is broken out, snow is broken out, and seismic is broken out. I've pulled them out for you and assembled them in this table. This table is also available on Quarkus, so you can download this as a PDF as well. Low, don't even think about it. Let's just do it. Most of the time, it's regular. We are going to put a 1 in front of everything that we're designing for strength. If it's high importance, so that means maybe a community center or a school where people would gather after a disaster, we would say wind, we're going to increase the load by 15%. Snow, we're going to increase by 15%. Seismic, we're going to increase by 30%. Post-disaster, we go up even more. We also have importance factors for serviceability. So look at this: strength, ULS, ultimate limit states design. Deflection and serviceability, serviceability limit states. So this, strength, life safety. We want people to survive, so we're factoring these things up. Deflection and serviceability, that's not about life safety. That's either about people's comfort level or it's about preservation of finishes. And if after a gigantic snowstorm that people are seeking refuge in a community center, if our drywall cracks a little bit, we're okay with that. We can live with that. We accept that in a worst case disaster, we might have some damage. So what we say is that wind load for serviceability, it doesn't matter what criteria it is or what category it is, we design it to 75% of the design load. Snow, we design it to 90% of the design load for serviceability. Well, let's take a look at our first climatic load, or one that is imposed on our building from the environment. The way these loads are developed is that statisticians and meteorologists look at all the data from as long as we've been recording data, they track it, and they figure out the statistical probability of the worst case storm, or they figure out what statistically the worst case storm would be in a given 50-year time slot. And that is what we design for. Don't worry, we still have load factors to come. We still increase it even more than that. So we figure out what our snow load is, and then if it's high importance, we multiply it by we add another 15%, and if it's post-disaster, we'll add another 30%. And then we'll talk about load factors in a few slides. So, sorry, I went for a run today and my legs are a little bit sore, so I'm squirming around a little bit. So, the design snow load is something we have to calculate because there are some things that affect the snow load that are based on our building, that we're picking, that we know about our building. What the statisticians and the meteorologists give us is a ground snowfall value in a particular area. And that is something that we would pull out of climatic data. I have provided for you the climatic data in the building code for Ontario. In that, they will give us two things. They will give us SS, which is the 1 in 50 ground snow load. So in a 1 in 50 year worst case snowfall event, that is the weight of snow that would sit on the ground. SR is the associated rain load. That is not to be confused with a rain load, which we are going to talk about in a minute. The associated rain load is, I think of it as the wet factor within our snow. So how wet is your snow? What is the odds that in that big snowfall, you will have a certain amount of moisture embedded in that snow? That is different from a rainfall or a rain load. This is the rain load squished into your snow load. So the snow load is your importance factor for snow times, in brackets, your 1 in 50 year ground snow load, some factors, plus your associated rain load, and that's the value. So what are the factors that could impact our ground snow load? Well, one is the basic roof snow load factor. So what they say is, have you ever been baking and you dump your flour into the bowl, and some of it inevitably, it doesn't matter how careful you are, some of it inevitably ends up on the counter around you. If you pick that bowl up, even if you dumped it right in, if you pick that bowl up, you'll see an outline of your bowl on the counter. It's inevitable, it always happens. That is the reduction factor that takes out all the stuff that doesn't stay on our roof. You can imagine if you dumped that flour on a flat surface on top of your bowl, even more would come up. So CB is the basic roof snow load factor. CW is the wind exposure factor. Actually, let's flip to the next slide. So CB, the basic snow load factor. It is 0.8 for all Part 4 buildings. We are doing Part 4 buildings. We are not looking at Part 9 buildings. Part 9 is a section of the code where we don't really do a lot of design. It is mostly pulled from tables and lists and is usually applicable to small-scale residential construction. Why do I put this in here? Why do I even list it? Because it exists and people ask me about it. What I don't want you to do is use 0.6 as your CB value. In spite of me saying, do not use this, whatever you do, don't use this, people will use it in their calculations and get the wrong answer. In the grad course, I show this same slide, and people do it in their final project, where they have to just calculate the snow load, and they get it wrong, because they use the thing that says, does not apply to this class. And I am truly baffled by it. This one is what we are going to use 100% of the time in this course. We're going to use 0.8. CW is the exposure factor. This says If our building has snow on the roof, if it's a really windy spot because there's nothing else around it, some of that snow is going to blow off the roof. Again, typical. 1 is typical. 0.75 is when we're exposed to winds on all sides. If you look at the code and look at this clause, it says with no obstructions within a 1 kilometer distance from your building. I cannot think of a single building that has no obstructions, and it doesn't mean it has to be higher than it. It can be lower than our building. There just has to be nothing around your building. So no trees, no buildings, basically in a flat open parking lot. So maybe something that had paving for a kilometer all the way around it, you could use it. So again, 1. We are going to use 1 100% of the time in this course. CS is the slope factor. So we have, I feel like I should have something more rigid right here. This is it. Okay. We have snow on a flat roof. It's all going to sit here perfectly like this. As we tilt it up, the snow's pretty sticky. It doesn't really slide off very easy until we get to 30 degrees. At 30 degrees, we say it starts to slide off. Some snow will start to slide off of this. If we tip it all the way up to 70 degrees, we're saying no snow can stick to this roof. It's all going to slide off. It's all gone. So 30 degrees, we still use the full snow. 70 degrees, we use none, and we vary linearly in between. So at 30 degrees, it's 1. At 70 degrees, it is 0. So 70 minus 30 divided by 2 plus 30. At 50 degrees, that was silly, I could have done that in my head. At 50 degrees, CS would be 0.5 because we're varying linearly between these two values. Most of the time, we're going to be under 30 degrees. In Ontario, the loss of space you get that you have to heat and do stuff with to diminish our snow loads isn't worth it. People get all excited saying, I'm going to make an A-frame here in southern Ontario. Well, the cost of the extra material to do that doesn't gain us anything versus the dropping the snow off the roof. It actually ends up costing more. In northern regions or mountainous regions where the snow loads are much, 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 much higher, there's an advantage to trying to build a structure that forces the snow to fall off. In fact, that's the idea behind kind of the onion domes in Russia. So, SS and SR, I said these are 1 in 50 year probability occurrences, and we look it up in the climatic data. So this is published information. We look up SS and SR, and I've provided that for you. Here, for example, is Toronto City Hall. Snow load KPA 1 in 50 years. SS is 0.9, SR is 0.4. There was one more factor that we didn't talk about, and that's the accumulated snow load factor. We are not going to use it. We are going to say that it is 1. For everything we do in this course, our accumulated snow load factor, or our CA, is 1. We're just not going to worry about it. But why would we have an increase in snow load? Well, if this is our snow falling flat on the ground, no problem. Sitting on top of our roof, we've applied our CV factor of 0.8. So remember, that's our basic roof factor. We have a flat roof, so our slope factor is 1. We have other buildings around. There's some trees right here, so our CW factor is 1. If I was going to make you do this, this is why we would use something different than 1. You've all seen this. Beside a higher building, you get snow accumulation. Around a mechanical unit, you get snow accumulation. Beside a parapet, you get snow accumulation. So all of those would cause snow accumulation. Do you guys remember in that typical steel and concrete drawing I showed you, we had a varying sloped snow load? Well, that's because it was a low roof beside a high roof, and we had kind of this condition of snow load buildup on that low roof. So let's do an example. What is the snow load on the flat roof of a Toronto condo if there are no buildings taller than it nearby? So, let's see how handily this is going to go. I purposely bought this new stand so that I could do this easily. And this is the first test of how easy it is. Okay, so we know it's in Toronto and it's a condo and there's no buildings taller than it nearby. Let's make my paper bigger here. Okay, so we have a building in, oh, Dave has used this pen. He ruins my pens. Oh, he's ruined this one too. Let me get a better, maybe I've hidden this one well enough. Ah, he's ruined this one too. I have to get out a brand new one. Okay. All right, so we have a building in Toronto. So we know that this building is in Toronto. We know that the equation for snow load is snow load equals the importance factor for snow times SS, which is our 1 in 50 year probability event, times CB times our CW times our CS times our CA plus 0.4, and then that's inside that bracket. So there's 2 layers of brackets here. Remember your order of operations. Let's figure out what these values are. IS. Well, that's the importance factor. You know that this is just a regular old condo. Why would we think that it would be anything else? So it is 1.0 for ULS. Remember, we had 2 different importance factors. We saw for serviceability, though, the importance factor for snow was 0.9. So we have 2 different importance factors. So we probably have 2 different things we need to calculate. Snow load for strength and snow load for serviceability. Well, the snow load that we looked up in the climatic data tables for Toronto, we just saw it, and this is City Hall. There's nothing telling us otherwise. We're going to assume it's not Scarborough, it's not North York, it's not Etobicoke. We've got Toronto, good old Toronto, right downtown. They told us that it was 0.9 kPa, and also in that we had our associated rain value. So not rainfall value, but our associated rain value as 0.4 kPa. CB, we know, is 0.8. I've told you, don't use anything else. CW is our wind, basically wind scour. What are the odds that the wind's going to blow it all away? I've told you, it's almost always 1. CS is our slope factor. Well, we've got a flat old roof here, so it's 1. And CA, I have told you, well, it said in the question that there are no buildings taller than it, beside it, so we can't have accumulated snow loads. That doesn't mean this is 0, that means this is 1. So let's calculate our snow load for ultimate limit states. Our IS is 1 times our SS, which is 0.9, times CB, which is 0.8, times 1, times 1, times 1. So that's CB, CW, CS, CA, plus 0.4, and we end our bracket. And we can plug this into our calculator, and we get 1.0 times a bracket, 0.9 times a bracket, 0.8 times 1 times 1 times 1 end bracket, plus 0.4 end bracket. We get 1.12 kPa of snow load on our roof. We have another thing we have to calculate. Our serviceability snow load. The only thing that's different, all of these things stay the same. The only thing that's different is now we have 0.9 times 0.9 times 0.8 times 1 times 1 times 1 plus 0.4 end bracket, or 0.9 times 0.8 plus 0.4. Oh, I didn't do my second bracket there. So we have 0.9 times 0.8 plus 0.4. Alright, 1.12 times 0.9. We have 1.01 kPa. So for strength, we would design for 1.12 kPa, and for serviceability, we would use 1.10 kPa. So I mentioned rainfall. So rainfall, we are not going to, I'm huge in this, let's come back, because you guys can't see the next slide. All right, so here that's worked out for you again, so you can see it slowly. Rain load. All roofs need to support the 24-hour rainfall. This only tends to govern if there's a large slope to a drain where the rain can accumulate. And why is that? So in that same chart, it gave a 24-hour rainfall value. I think in Toronto, 96 millimeters or something like that, and that's a 1 in 50 rainfall event. I know that in Toronto, regions of Toronto in 2013 got 121 millimeters of rain in 2 hours, far exceeding their 1 in 50 year rainfall event. It doesn't tend to govern for us here in Toronto because the snow loads are higher, but why do we worry about it? Well, this is the volume of rain in 24 hours. It doesn't matter what the shape of that volume is, it's the same volume. So if we have a roof with a drastic slope on it, that same volume gets positioned like that. Well, you can imagine if we have a beam here, and a beam here, and a beam here, and a beam here, they're all supporting the same depth of water above them. But here, we have a beam here, and a beam here, and a beam here, and a beam here. This beam right here is supporting an awful lot of water. I have only a handful of times had the rainfall value govern my beam design. Again, you are not going to have to calculate this, but I just wanted to show you it exists. Wind. I am also not going to make you calculate wind loads. I'm going to tell you where they come from and the idea behind them. We have quite a bit more to get through in this lecture, so I want to make sure we leave time to talk about it. Wind loads. We have winds blowing on our building. There's a unique thing that when the wind blows on the building, it pushes on this side, and it actually causes suction on this side. While it's going over the roof, it can cause wind to blow down on the roof, or it can cause suction on the roof. So we look at the building as a whole with those winds pushing on it and pulling on it in the same direction. We look at the roof for downward loads or uplift, and then embedded in the wind load is something called a gust factor. If you've ever been standing outside and you can see the tree over there blowing really hard with the wind, and then it stops blowing, and then a few seconds later you get a blast of wind on you. Well, that's because localized spots will have really high wind loads. The idea in a building is that the whole building being designed for the loads might have spots that are seeing gusts, but you're averaging it out over the whole building. That particular element, though, needs to worry about that high gust load, but we don't apply the high gust load over the entire building at the same time. When designing the building, we would just design it for each little element at a time. The wind load calculation is very similar to the snow load, where Q is the reference wind pressure that we would look up in the climatic data tables the same way we did our snow loads. P is our wind pressure in kPa. IW is our importance factor. Remember, we have two. We have our strength and our serviceability factor. Wind factors. The exposure factor. So this says that we are exposed. I often use the exposure factor as 1. I just found out that Dave in the city actually uses the reduced one. I'm not going to do that. We're going to say that it is hard to achieve. As much as we say for snow, our building is sheltered, for wind, we say it's pretty exposed. So kind of the worst case of both things. For CP is the pressure coefficient. That's really dependent on the type and shape of the building and way beyond what you need to know about. And the gust factor I just talked about. So Q is the 1 in 50-year reference pressure, wind pressure used for the design of the strength of the structure. Here we are. So we already pulled off SS and SR. We looked at a one-day rain, 1 in 50-year rain. So remember I said Toronto City Hall was 97 millimeters, but Etobicoke was 108. And Etobicoke is where they got the 121 millimeters a couple years ago. What we're talking about now is this 1 in 50 hourly wind pressure. So Toronto City Hall, 0.44 kPa. The States does it in a slightly different way. They give it in a velocity, which would be like a kilometers per hour. We also do it as an hourly wind pressure, and they do it as a velocity 3-second gust value. So if you want to work things back and forth between the codes, you do have to go through 2 stages of transferring it. So you would need to change the gust to an hourly wind, and you would need to change the velocity to a pressure. Again, we're not going to do any calculations on that. Interior wind loads. Okay, so inside a building, we do say some wind gets in through the walls of the building, but we also have differential pressure between rooms that's generally caused by an HVAC system. Some rooms get kept under positive pressure or negative pressure to relieve or relative to the surrounding rooms. That ensures a one-way airflow in or out of a room. So if you have an exhaust system somewhere else, you're forcing your airflow to go in a certain direction. That's really all we're going to look at for wind right now. Seismic, again, is beyond the scope of this class. Oh, I meant to throw a video in here of really what seismic load is doing. So slide 41, video. I have an awesome video that really shows what seismic load is doing. So seismic load is when the ground lurches around and your building's trying to stand on it. It's like trying to pull the rug out from under a building. And the video I have is my 2 boys this summer standing on one of those yellow swim mats, and my husband literally pulls the mat towards him, and they're both standing there, and they can't stand up, and they fall to the mat. They had a great time doing it. We spent an hour doing that with them, but that is what's happening with seismic load. I tried really hard to get a video of them turning and bracing their feet when he did it, to see that they wouldn't fall over, but they were having so much fun playing the game that they refused to do it. Basically, what we're saying is that the heavier something is, the more likely that when you yank the ground out from under it, it will try to tip over. I know you're thinking, but it's heavier, so it wants to stay still more. it also means that the acceleration of the ground trying to pull it this way leaves the top kind of stuck hanging there, and it tries to topple over. So a heavy building sees more seismic loads. Seismic loads is one of the few spots in structural engineering that we are making huge advancements in today. Engineering, most of what I'm teaching you, the science behind it hasn't changed in 150 years. Well, maybe more than 150, but somewhere around there. But seismic loads is one of the spots where our understanding and the way we design for it has advanced hugely. We used to do a very simple calculation. We used to say that the effect of seismic loads, depending on where you were and the probability of seeing a specific seismic load, was dependent on a percentage of the weight of the building. The heavier the building, the more force we have acting on it to try to topple it over. And that, I really think, is the extent of what you guys need to know right now. Soil pressure. I am really talking a lot in this lecture, and I don't want to cut it short because your assignments and quiz are made. Soil pressure. All right, so soil pressure is this one where I was talking about where if you dig a hole and someone stands on the edge of it, the soil tries to fall in. Well, what happens if no one stands on the side of it, but you try to dig deeper? Eventually, the soil tries to fill in the hole. Instead of adding a weight on it, what's happening as you dig down, the weight of the soil beside it is the thing trying to get it to push into the hole. So what we say is that the pressure trying to, out here, so all of this soil is trying to get inside our building. But we have a concrete wall here stopping it. We've braced it here and we've braced it here. And we want to know what the pressure this soil is putting on our wall. Well, the equation for the pressure of soil is KQ plus K gamma H. Now, K is not the same K that, or Q is not the same Q we saw for wind pressure. This is our live surcharge that would be happening right about here. Earth pressure is happening at a particular height. So this is to calculate the pressure at a particular height going up the building. And this is where we would infill height. Pressure, so that earth pressure is what we're trying to calculate at a particular height. K is the earth pressure coefficient. I think of it as the soil sticky factor, or how cohesive the soil is. If the soil is really sticky, it's less likely to try to fill in that hole. If it is, so it's actually kind of an inverse value. The higher the value, the less sticky it is. The lower the number, the more sticky it is. Don't worry about that too much. Q is the live surcharge, or what's happening right here. If right beside your building there's a laneway, well, that means a big old fire truck could come down here, and our surcharge is going to be 12 kPa. Otherwise, any building ever could have people, an assembly load happen right outside it. So it would be 4.8 kPa or 12 kPa if we're in an alley where a fire truck can get down there. Gamma is the weight of the soil. So remember I said the further you dig down, the more likely it's going to try to fill in the hole because the weight of the soil gets heavier, the weight or the amount of soil above you increases, meaning you have more force trying to fill in the hole. And then H is the depth, the low grade. So we have two parts. We have the soil stickiness factor times the surcharge, and we have the soil stickiness factor times gamma, which is the weight of the soil, times the height. Let's take a look at a quick example here. We have a house in a basement. It's a 10-foot basement. The soils report tells us that the earth pressure coefficient is 0.3, so that's K, and the soil has a weight of 20 kilonewtons per meter cubed. That's gamma. Assuming there is a laneway adjacent to this house, so that means we know our surcharge should be 12, what is the soil pressure at both the top and the bottom of the wall? So let's make my calculation pad bigger here for you. So let's look at pressure. So we have soil here with a wall of some sort. And we know that there can be a fire truck here. This dimension is 10 feet. Well, right away, let's transfer that into meters. Let's just make that meters right away. We know that 10 feet is 12 inches. So 10 times 12, 1 foot is 12 inches. So that's 120 inches. And we know that 1 inch is 25.4 millimeters. So 120 times 25.4 is 3,048 millimeters. And we know that there are 1,000 millimeters in every meter. So we know that that height is 3.048 meters high. We know that the equation for pressure of the soil is KQ plus K gamma H. They have told us that K equals 0.3. We know that Q, which is the surcharge, is 12 kPa because we have a laneway, so we could have fire trucks there. We know that gamma equals 20 kilonewtons per meter cubed. They gave us that in the question. And H1 is at the top, so 0. So let's call that top, and H bottom is 3.048 meters. So this is H at the top, and this is H at the bottom. Let's calculate P at the top. We have K equals 0.3 times our surcharge plus our K times our gamma times our height. Well, the height at the top is 0, meaning we have 0.3 times 12, or 3.6 kPa. Let's look at the P, or the pressure, at the bottom. So this is the force trying to push in on our wall. We have 0.3 times 12 plus 0.3 times 20 times our 3.048 meters, or 0.3 times 12 plus 0.3 times 20 times 3.048. We have 21.9 kPa. So that means this pressure, I'm going to use a different color here. The pressure trying to push in on this wall varies from 3.6 kPa all the way down to 21.9 kPa. Do you remember that Arnold was 1 kPa and our live load assembly loads was 4.8 kPa? Soil is a gigantic load, and it's everywhere, all the way around the base of this building. This is why we like to do one of the reasons we like to do our foundations in concrete. So let's bring this back up here to me. I'll make me smaller. How are we doing for time? Woohoo, tight. Okay, here's that worked out again. There are a few other types of loads that we worry about. Temperature. Most of you know that things expand when they're hot and they contract when they're cold. It's not often that we have to worry about this because most buildings are of a scale that it's not something to be concerned about. But on large scale buildings, or buildings where we have part inside and part outside, or if we have buildings or structure that is outside, normally we're inside an envelope. So it doesn't really matter. Our temperature is going to be pretty steady, somewhere between like 14 degrees and 30 degrees, in the realm of normal. But if something is outside, we could see changes from, minus 10 to 20 degrees over several hours. And that's when we need to worry about the expansion and contraction of our steel elements. Again, it's not a normal thing to worry about. It's usually in large buildings or ones that are partially inside, partially outside, or under construction will be outside for a long period of time. Pre-stress. Pre-stress is where we know that we can't, so pre-stress is when we tighten something to prepare it to take load. So if we pull it tight, if we pulled my elastic tight, for example, somebody could push on it. And rather than it buckle, we would just unload it until, all of a sudden we got to the point where it would buckle. If anyone has tried to use one of these saws without this handle pulled tight, this saw tries to buckle when you're trying to saw. The saw blade buckles when you're trying to use it. That act of pulling it like that is what causes this to be pre-stressed so that you can use it. Vibration. Vibration is something that we worry about. It's mostly about people's perception of how the building feels. So we don't spend too much time on it for most elements in a building. We worry about continuous vibration, which is people moving around. I talked about this last week. Or damping, which is where we have an impact load that shakes out through the building. We do worry about it with amplification, though. Amplification can be a life safety issue, but it's under very specific circumstances that would be created. So you guys remember, the load on the system times the factor of safety needs to be less than or equal to the capacity. We factor up the load, and we reduce our capacity. So we factor the load and we reduce our capacity, and that factored load needs to be less than the reduced capacity. And that little symbol F means we factored it, and that little symbol R means we've reduced it. That is called limit states design. Our strength is our ultimate limit states design process. Or ultimate limit states. So that is all about life safety. So strength is all about life safety. If you see this ULS, we're talking about life safety. If you see SLS, we're talking about deflection, not about life safety. It's about preservation of finishes and comfort levels. So if we have a disaster, we don't care so much if some drywall cracks. We want everybody to stay alive. So what are the importance factors? I have a feeling I'm going to go over a little bit today, team, and I apologize about that. I'll try not to do that going forward. I know your time is valuable and precious. Feel free to, if you don't need to make use of the entirety of the tutorial, skip over and listen to some of this during the tutorial time slot as well. The tutorial used to be taken up a lot with them going through the answer sheets, but I now provide you with the answer sheets for the quizzes and the assignments. So that might cut some of the time that you might have needed in the tutorial that you could take up by watching some of this. So what are the load combinations? Well, here I have for you the ultimate limit states load combinations. Here we have principal loads, and then we have some companion loads. So, all by itself, we multiply dead loads by 1.4. Here, in our next line, we multiply dead loads by 1.25. Don't worry about the or 0.9 right this second. And then we add on 1.5 times the live load. If with the live load there is also snow or wind, we will add 1 times the snow load or 0.4 times the wind load. This 1 is a change relatively recently, so most of my slides and lectures have only had this adapted in it over the past year. We could have, so this is live load as our principal load. Here we have dead with snow as our principal load, so 1.5 times the snow, plus, if we have it, 1 times the live load or 0.4 times the wind load. You wouldn't do both of these. We have another case of 1.5 times the dead load plus 1.4 times the wind load as the principal load. And then we would add on, if they happen to occur, 0.5 of the live load or 0.5 of the snow load. We then have our seismic condition, which is our dead load plus our earthquake load plus our 0.5 of our live load plus 0.25 of our snow load. So those are our load combinations. You'll see we also have a 0.9 dead load. We use that when we have something that might be benefiting us. So let me think of a good example for this. Okay, this is our braced frame here. This brace right here under dead load would have some compression load on it. If I put a heavy load right here, most of it's going into this, but some of it's going into this, so I'm pushing down. If I have wind load blowing in this direction, I have tension on this brace right here. That means that if I'm looking for the worst case tension on this member due to the wind load, my dead load is taking away from my tension load. And if I take away 1.25 times the dead load, I could be overestimating the helpful benefit of the dead load on tension for this brace. Those are the conditions where we would use 0.9 times the dead load. If we think the dead load is helping our load and not letting us look at the worst case value, because remember, we want to make sure the worst case factored load is less than the capacity. So we're going to figure out all these load combinations to find the worst case one. Figured out how I'm going to handle some of this. Okay, so let's take a look. Load combinations. We can have 1.4 times the dead. We can have 1.25 times the dead plus 1.5 times the live. We can have 1.25 times the dead plus 1.5 times the snow load. We can have 1.5 times the dead plus 1.4 times the wind load. So this doesn't have any companion loads. These are just the principal loads. Well, we could also then have the principal loads. So when I have live as the principal load, or sorry, companion loads. If I have live as the principal load, I could have snow as a companion or wind as a companion. If I have snow as the principal load, I can have live as the companion or wind as the companion. If I have wind as the principal load, I can have live as a companion or snow as a companion load. And then, what if I have a condition where I have wind causing uplift on it, and I don't want to assume I have more dead load, because then I could be underestimating the tensile load on something. So I'd look at 0.9 dead plus 1.4 times the wind load. And then I have quake without my companion loads, and then I have quake with my companion loads. So that's a lot of load combinations. But what about the fact that wind and earthquake need to be analyzed in each direction of the principal axis? So we can have wind going in this direction, and we can have wind going in this direction, or in this direction, or in this direction. That means for every wind case, we actually have 4 wind cases. And for every seismic load case, we actually have 4 seismic load cases. So we have to add all that in. This doesn't even take into account that when we design seismic and wind, we actually put a little bit extra load on the ends sometimes to account for the possibility of it twisting. So we would actually have end zones, wind and earthquake loads that we would worry about, which means for every one of these wind cases that we already have, we'd have double. And for every one of these earthquake loads we'd actually have double. I have done projects where I have had 1,250 load combinations I needed to worry about. And every member of the entire building needs to be checked for bending, shear, and axial loads for all 1,250 load combinations. That's an insane amount of bookkeeping. That's why software helps us out a lot, and knowing what might be the worst load case. We also have serviceability limits. So, serviceability for roof deflection, we would have our dead load plus our snow load. But remember that this snow load, we would need to be using our SLS snow load, which had the importance factor of 0.9 applied. So it's not our ultimate limit states snow load, but our serviceability limit states snow load that we would have already calculated. So floors for deflection would be dead plus live, or live by itself. We have our foundations here, and for building movement, for wind, we would apply our 0.7. We would need to make sure we used our serviceability wind load. We are not going to make it as complicated as all of that. We're going to do one example where we look at the load combinations on an element. We're not quite sure what the element is, but they've told us that it could see dead of 12 kilonewtons of compression, live 10 kilonewtons of compression, snow 5 kilonewtons of compression, or wind with 10 kilonewtons of compression or tension. We want to look at our factored loads, or ULS, our serviceability, or SLS, load combinations. So let's do that quickly, and then I will wrap up this lecture, and then I'll treat tributary area as a tutorial time slot component that you guys can watch. You don't have to watch it during your tutorial, you can watch it separately, but we will have elements on the assignment and the quiz that will touch on the tributary area and tributary width. I used to not even do the next component in the lectures, but because most people intuitively know it, there was enough people I found over the years that really struggled with that basic concept that I decided to make it a whole little module within a lecture time slot. But we don't have that many lecture time slots, so I've got to try to jam these things in. So let's take a look at this load combination situation here. So we'll do this, and then I will make another video about our tributary areas and tributary widths. How is, there. Okay, that's a little bit better. All right, so I will make us big here. All right. So like I said, this could be a much shorter lecture, but I think examples are really, really, really important, and I don't want to deny you that. So let's look at our factored combinations, or our ULS combinations. Well, we have our ultimate dead case, or 1.4 times our 12 kilonewtons, our ultimate dead live, or 1.25 times 12, plus 1.5 times 10, our ultimate dead snow, or 1.25 times 12, plus 1.5 times, what's our snow? 5. Ultimate dead wind, and I'm going to do just the downward forces for right now, plus 1.4 times 10. I think you can see at a glance that this one's probably going to be the worst case one. Normally I would plug all these into my calculator, but we're running low on time. So I'm going to just start filling these in. You can plug these in if you'd like. So we can see already that the ultimate dead live seems to be the one that's governing. But remember, we have to worry about those companion loads all of a sudden. So we can do ultimate dead live with snow as the companion. So 1.25 times 12 plus 1.5 times 10 plus 1.0 times 5 equals 35 kilonewtons. I think you're starting to see the idea here. We can go through and do all of these, and you guys can see those all worked out. I just want to make sure we don't run out of too much time here. I want to jump down to the ultimate upward dead wind load case. I just use this little u to say I'm talking about the other direction now. Well, for this, remember, wind could be in tension or compression. So for this, we're saying that our wind is going in the other direction from our dead load. So we're going to do 0.9 times our dead load minus our uplift force, or our tension load, of 1.4 times our 10 kilonewtons of wind. And we end up with minus 3.2 kilonewtons of tension. In all of the other cases, we had downward loads, and this one ended up being the worst case. You can see it, they're all worked out in the slide. And upwards, this is our worst case. So our worst compression, or our factored compressive load, is 35 kilonewtons. And our worst tension load, or TF, remember, compression is squashing, tension is pulling. Our worst tension load is 3.2 kilonewtons. So we will need this to be less than CR, and we will need this to be less than TR. I'm going to stop writing the equals to because nobody ever writes that, but this is what we're saying. We need to now figure out what the worst case compressive resistance and the best case, we need to figure out the compressive resistance and the tensile resistance and make sure they're greater than our factored loads. If you jump over to the serviceability portion of this, so you can see that this is all worked out here. You can see all those steps. For serviceability, remember, all the factors were 1, but we needed to use our importance factor of 0.9 for our snow load and 0.75 for our wind. We were assuming that it was a regular building because there was nothing telling us otherwise. So we would take that load we were given and reduce it by 10% here and by 25% here. And that would allow us to figure out our serviceability limit states loads on that same element. Now, for serviceability, it's not about picking the worst case element. We're comparing it to a specific criteria for that load case. Remember, we had a different criteria for dead and snow together than we did for snow all by itself. So it's important that we compare these to different criteria. You're saying compare it to what? I don't understand what she's talking about. I know. We'll get to that later on. We have to do this in steps. But I've given you the means now to figure out what your factored loads are and what your serviceability loads are. Sort of. I mean, the ones I'm giving you are not going to be that hard. I'm not going to make it wild and crazy on you. It's going to be something very similar to this. But you can see now that we are factoring different things. Okay, so we're definitely over, and I very much apologize for that. I am going to do, as a tutorial component, tributary areas and widths. So I will do this. It's just a few slides. I'll do that as a little separate mini video to talk about tributary area and width. So the things you'll need to know is how to look up your live load based on the building and room type, how to look up your dead load once you know what the assembly is, You should know that snow and wind and seismic are based on statistic probability and how to calculate snow if I give you a chunk of information. You should know that soil, temperature, pre-stress, and vibration loads exist. You should know that loads are combined and factored for the worst case ULS, and we look at SLS. And then we will talk about the tributary area for elements in a tutorial segment. And you should have a general idea of what structural drawings look like. So I know this was a lot of load, or a lot of information, but I like to think that it's because I am providing you more information. I used to do this lecture in exactly an hour and 55 minutes, so that just means I've given you more information. So in one side I apologize, on the other, you're welcome for the extra information. So I'll create that tutorial tributary area and width section now. All right, have a great week.